Welcome to Study Loop.
Okay, this is Chapter 11, Section Problem 92, and this is a longer one. Butane, C4H10, has a heat of vaporization of 22.44 kilojoules per mole and a normal boiling point of minus 0.4 degrees Celsius. A 250 milliliter sealed flask contains 0.55 grams of butane at minus 22 degrees Celsius. How much liquid butane is present? And what if you warm it up to 25 degrees Celsius? How much liquid would be present? So what we have to use here is the Clausian-Capron equation. And I will point out that there's a really great example and set of calculations that are really similar to this problem on page 486 of the textbook. It's example 11.5. So you could see that practice problem for kind of a similar walkthrough. Nevertheless, here we go. So the form of the equation that we need is the natural log of P2 over P1 is equal to minus delta H vap over R times 1 over T2 minus 1 over T1. And really what this equation allows us to do is calculate different vapor pressures at different temperatures because, you know, we have butane at a different temperature than the boiling point. So it's below the boiling point, so there's going to be some liquid, but we don't know, right off the bat what the vapor pressure is at that temperature. So that's what we have to do first, is figure out what the vapor pressure is at that temperature. And this is the equation we use to do that. Okay, so there's some things that we can pull out of the question itself. So the heat of vaporization is 22.44 kilojoules per mole. And the temperature, the T1, is the normal temperature of the boiling point, which is minus 0.4 degrees Celsius. And whenever you're doing calculations and you have to actually plug in the temperature, you got to convert that to Kelvin. So, minus 0.4 plus 273.15 is going to give you 272.75. So that's our T1. Our P1, the pressure, the normal pressure is just atmospheric pressure. So that's 760 millimeters of mercury. And the other thing we got to calculate before we really start the main calculations is that T2 in Kelvin. So minus 22 degrees Celsius plus 273.15 is going to give us 251.15 Kelvin. You got to pick a gas constant, and because they give us kilojoules for our delta H vap and moles, we can use 0.008345 kilojoules per mole per K as our gas constant. And, just as they do, as I mentioned in that example, example 11.5 on page 486, we can do some rearranging and simplification before we find our final answer. So the natural log of P2 over P1 is going to equal, like I said, this. So we can plug in the value for the heat of vaporization, which is 22.44 kilojoules per mole, and multiply that, or rather divide that by our gas constant, our R, 0.008345 kilojoules per mole per K, and then multiply that by 1 over T2. And again, our T2 is the temperature that we're trying to find the new vapor pressure for, which is 251.15. So multiply that by 1 over 251.15, and then subtract that by the T1, which is 1 over T1. So that'll be 1 over 272.75. Okay. So when you solve that, it gives you minus 0.851. And we can do, drop the logs. So when we drop the log on the left, that means we have to, on the right side, we take E and raise that to the power of, what that was. So P2 over P1 is going to equal E raised to the minus 0.851. Multiply P1 by, on both sides, and plug that in, being 760 millimeters of mercury, so times E raised to the minus 8.51. And solve that, is going to give us a vapor pressure at minus 22 degrees Celsius of 324 millimeters of mercury. Okay, so that's the pressure of the gas at that temperature. So what the actual question is asking us is there any liquid left over? So we take that pressure and plug that into the ideal gas law to find out the number of moles of butane that is equal to, and then convert that into grams and go from there. So PV equals nRT is the ideal gas law. So rearrange it to solve for N. And so N is going to equal PV over RT. And so the pressure, again, is that vapor pressure that we just solved for, times the volume is the total volume of the system, that being 250 milliliters, so that's 0.25 liters. Now we divide that by R, which is, as I mentioned before, we've got that in units of millimeters of mercury. So it's divided by 62.364 liters millimeter of mercury per mole per K, and then multiply that by the temperature. And again, this is the temperature, it's like T2. So that's our 251, that's our 251.15. Okay, plug that into your calculator, and that's going to give you moles of butane in the gas form maximum. And then we convert that into grams by multiplying it by its molecular weight, which is 58.12 grams per mole. And we see that at that temperature, only 0.301 grams of butane are able to be in the gas form at that temperature, which is less than the original 0.55 grams that were given. So do a subtraction there, and we calculate that actually, under the first set of conditions, there's 0.249 grams of liquid remaining. So that's half of the question. And by the way that the question was worded, because we started with a lower temperature, then we went to a higher temperature, they kind of gave it away that probably we're going to have some liquid left over. And, probably, just guessing, it's the second part of the question is going to be, there's going to be no liquid left. And that turns out to be true, but we still got to do the calculation. So it's exactly the same, except we got different numbers this time. Okay, so the T1 and the P1 are exactly the same. The delta HVAP is the same, but now we have a different T2, which is room temperature, or 298.15 Kelvin. Again, the R is the same. So really, the only thing we're changing here is this T2, where we're raising it now to 298.15 in our calculation. That does change this number right here, and subsequently the rest. And what we'll see is if you plug this through and work it through, the vapor pressure now is much, much larger. So at 25 degrees Celsius, now the vapor pressure, which is the maximum pressure available to the butane, is 1766 millimeters of mercury. But we still have to go through and see if we have enough, butane to make that amount of pressure. Plug it into the ideal gas law, just like before. So the number of moles is going to equal that pressure times the volume divided by the our gas constant that we chose times the temperature. This is another place where the calculation is a little bit different this time. And we see that now we're able to have significantly more moles of butane in the gas form, 0.0282 moles of butane. Again, that's maximum. And if we multiply that by the molecular weight of butane, 58.12, we see that actually it's 1.64 grams of butane would be in the gas form in a 250 milliliter sealed flask, which is more than we started with, right? We started with 0.55 grams. So because we actually have less butane total than is able to be in the gas form due to the vapor pressure at that temperature. In the second scenario, there in fact is no butane in the liquid form. Yeah. Anyway, as I mentioned a couple times, really a straightforward explanation of this, in addition to just what I've provided, is on page 486 of the textbook. It's example 11.5. So good luck.